For those of you that don't know me, I'm David Cantrell. I'm the chair of the Victoria Division for the Geological Society of Australia, and it's my pleasure to welcome you all here on behalf of both the Royal Society and GSAV to the 2015 Howitt Lecture. This is a joint lecture that the two societies put on together on a more or less annual basis, or we try to make sure it's an annual basis. Well, without any further ado, I'd like to get on to the course of this evening, the Howitt Lecture. And this year's Howitt Lecture is going to be delivered by someone that we all know well from a whole range of views across Victoria, Bill Birch. And Bill Birch was born in Melbourne, has lived in Melbourne for a long time. I'm not going to give away secrets there, Bill. Graduated from the University of Melbourne with a PhD in geology, and then went to Museum Victoria where he's curator of minerals. Started there in 1974 and retired fairly recently. His time at the museum's seen enormous amount of field travel, collecting, and the mineral collection at the museum's been built up and is, I'd say, one of the best in the world at the moment, and that's been due to the hard work of Bill and people that he's worked with. He's got an extensive publication record, 210 papers and articles at last count, and although he's retired, he's continuing to work in that space, and he's described more than 40 new minerals over the course of his career, so a real contribution to that whole field, and one that makes him well qualified to deliver this Howitt Lecture on Victorian gemstones. He has also contributed internationally, in particular the International Mineralogical Association for 30 years. He has been awarded the Selwyn Medal by the Geological Society in 1999, an AM in 2006, and most recently elected to President of the RSV here, and currently President. I don't know whether that's an honour or a burden at the moment. We have discussions from time to time about our roles as chairs of societies and what we need to do, but it's one that we both enjoy, and so I'd like to call Bill to the podium tonight to deliver the Howitt Lecture. Bill.
Thanks everybody. Thanks David. It's certainly an honour to give this talk tonight. I've never seen the theatre this crowded, so I hope I can live up to the expectations. First of all, I think we should have a slide about Howitt himself. We need to perhaps give a little bit of a brief on why we're holding this joint lecture. Alfred William Howitt was born in England, the son of William Howitt and Mary Botham, and he came to Victoria to the goldfields in 1852 with his father and his brother. Initially he was a geologist, and later he worked as a gold warden in North Gippsland. He went on to be appointed police magistrate and warden of Crown Lands Commissioner, and later still he held the position of Secretary of Mines. In 1861, the Royal Society of Victoria appointed him leader of the Victorian Relief Expedition with the task of establishing the fate of the Burke and Wills expedition. He went to Cooper's Creek, and there on the 16th of September 1861 he found John King, the sole survivor, and he buried the remains of Burke and Wills before he came back to Melbourne with King. And then he had a follow-up expedition to Cooper's Creek in 1862, and he recovered the bodies and brought them back for burial here. Howitt collected widely during his expeditions, and these collections are preserved in Melbourne. He was also a pioneer anthropologist, researching the culture and society of Indigenous Australians, and his magnum opus, The Native Tribes of South East Australia, was published in 1904. So he was a man of many facets, and both the Society, the Royal Society and the Geological Society hold him in high regard, hence this lecture, which I think has been held now for 10 or 12 years, something like that. Okay, now on to my presentation. Turn the lights down, you can all have a little nap. Now it's every author's prerogative, every speaker's prerogative to change the title of their talks at the last minute, which is what I've done. So it's basically the same, nothing's changed, but I've just called it Historical Perspectives and Modern Occurrences. Now 150 years ago this month, the people of Melbourne were treated to a wonderful exhibition of colonial gemstones and jewellery in this hall below us. It was opened by the governor. Tickets cost $1 to get in, and there were many personal collections owned by the leading people of the day. It was obviously a popular pastime, and there were major jewellery exhibitions as well. It received lots of publicity in the newspapers, and if you go onto Trove and look up Royal Society Victoria exhibition, you'll find there's a lot of articles. It certainly gained a lot of interest. And the Society published a full catalogue of the exhibition in 1866. So it was very well known and obviously highly praised. Melbourne Punch even went to the extent of putting a little cartoon in there, which you can all read. Who was responsible? Well, it was this chap. It was the Reverend John Ignatius Bleasdale, quite an imposing character. More about him in a minute, but at the time he was president of the Royal Society. He had a lot of power and influence, unlike today, of course. But but he went on a few years later to state that he thought Victoria was going to be the gemstone capital of the world. He was a great proponent of gemstones, but he was also very interested and influential in the wine industry, and more of that later. Just a few things about him. He was a Catholic priest, a chemist and mineralogist, born in England. He trained for the priesthood in Portugal and arrived in Melbourne in 1851. He immediately made his influence felt. He had a very wide interest in science, and he became president of the Royal Society, as I said, in 1865. He also had this interest in wine. Where he got those interests, we're not sure. Possibly in Portugal, but certainly the gemstone interest came out of nowhere, in a sense. He moved to San Francisco in 1878 and died in 1884. But I'll say more about him towards the end. There were other people involved. George Ulrich, a German-born mineralogist and geologist, came to Victoria in the 1850s, and he's had quite a significant influence. He was very interested in gemstones as well at the time. George Milner Stephen was a bit of a man about town. At one time, member for Colonial in the Victorian Parliament. And Edward Dunn was a young geologist who was living and raised in Beechworth in the what's known as the Ovens goldfield, and he was also collecting gemstones, and his collections that have been important in establishing or setting up this talk. They still survive from those times. Now, this is the contemporary painting of the Ovens, what's known as the Ovens goldfield, or the Beechworth Eldorado goldfield, where a lot of the gemstones were coming from, and where Dunn was wandering around getting diamonds and sapphires and other gemstones from the diggers. And this, of course, this scene would have been pretty typical of the times across all of central Victoria. Now, if we look at Victoria's gemstones, we have a very diverse geology. I'm not going to... So we have quite a wide range of gemstones, but because of the time, I'm only going to concentrate on the first three: diamonds, gem corundum, or sapphires and rubies, and zircon, because they're all in one way related. So the others, maybe some other time. First of all, diamond. Just a few general points about it. You all know it's a form of carbon, face-centered cubic crystal system, the hardest known natural mineral. It has a variety of crystal forms, often twinned, rounded, quite complicated. It's a gem mineral, and the 4 C's, carat, cut, colour and clarity, are all very important. Shows a variety of surface features which help tell you a bit about its history. The composition, a little bit of some trace elements go into it. Boron, replacing some of the carbon, will give blue colours, and nitrogen, replacing some of the carbon, give yellow colours. But that's all quite limited. And other colours like pink and brown are possibly due to strain in the lattice. Diamond also contains small inclusions, which are important for determining its origins. And there are broadly 2 types of diamonds. Those that are formed very, very deep in the crust under the old cratons or old continental masses, and then those that are perhaps not quite so deep, and they have a bit of organic carbon in them, and they have probably formed under what we call subduction zones, and I'll discuss those a bit later. Some typical Australian diamonds. These are New South Wales from Inverell. New South Wales had a diamond industry. They had enough of them. You can see these are colourless, quite rounded and lustrous, up to about 6 or 7 millimetres. These are Argyle diamonds, or diamonds from Western Australia, from the Kimberley region, showing the range in colours. And you can see there's a bit of a contrast in the type of crystal shape and colour. In Victoria, they started being discovered in the 1860, or the early 1860s. In fact, I mentioned George Milner Stephen. He actually must have been quite a gesture. He tabled a diamond in the Legislative Council in May 1860. Then they were started to be described. Bleasdale exhibited some at the Royal Society here in 1863. And there were 10 diamonds on display downstairs in 1865. All of them would have been from the Ovens district or the Beechworth district. And the Mines Department thought they were important enough to record. So between 1864 and 1879, they actually recorded in their annual reports when diamonds were discovered. Moving on to gem corundum, or sapphires and rubies. Very simply, it's aluminium oxide, hexagonal crystal system. They can show gem qualities when they're colourful and clear, but trace elements give them different colours, and I'll talk about that later. They have inclusions, which again I'll talk about later. They come from a wide range of metamorphic and igneous rocks. In Australia, in Eastern Australia, they're brought to the surface from deep below by basaltic volcanic eruptions. And they then get recycled into sediments, so they're widely distributed all over the eastern part of Australia. A couple of typical, these are rubies from Barrington in New South Wales. There was a small industry of these, the rough rubies and then some cut ones. These are the more famous, or the better known, Queensland sapphires, blues, greens, yellows from Anarchy, the Anarchy field, and some cut stones. What about corundum in Victoria? Well, again, just a few points. They were first found or recorded in 1854. George Ulrich described some coloured sapphires from Guildford in central Victoria in 1860. The Royal Society in 1865 downstairs featured quite a range of sapphires. The biggest one on record is a 17.9 carat from green sapphire from a place called Donnelly's Creek, which I'll show you later. We don't have many rubies, I don't think, if any. We have pink sapphires, but not rubies. And some of the early jewellers faceted them. These are some of the earliest recorded sapphires from a place called Blue Mountain near Trentham. And these were given to the museum in 1866. You can see quite well rounded. These are up to about 3 or 4 millimetres, quite small. Blue sapphires, well actually they're all sapphires, blue and pink. Now, it's rare to find sapphires enclosed in the basalt that brought them to the surface. As I mentioned, they get recycled into later sedimentary rocks because they're weathered out and they get moved around in streams. But they often, or they must have at some stage, been enclosed in cemented or cemented into gravels. And here we have a blue sapphire, perhaps 3 or 4 millimetres across, cemented into a gravel specimen. Now, unfortunately, this is Victorian, but unfortunately, I don't know where it's from. It's in the museum's collection, but it's probably Beechworth, but we're not sure. But this would have been one of the stages in the way sapphires were moved around. These are faceted Victorian sapphires, so as you can see, we've got the full range of colours, deep blues, pinks, green, yellow, and some unusual orange ones. These are from mainly historic locations. This represents almost the museum's full representation of faceted sapphires, so there aren't a lot. But I'm sure the gemstone fossickers have been more active in doing that. But just to show you the range in colour, probably up to about 7 or 8 millimetres across some of these stones. So they're quite nice. Moving on to zircon. Again, quite a simple chemistry, zirconium silicate, a tetragonal crystal system, highly variable crystal shape, and quite a range in colours. And in composition, it often has small amounts of uranium and hafnium. Source rocks, very wide range in rocks that it forms in. But it's been a very important mineral in geochronology. In other words, dating rocks, because you can use several methods, and I'll touch on those later on, fission track and uranium-lead dating. In Victoria, the earliest gem minerals reported again in the zircons in the Ovens district up at Beechworth. They're mostly red, called hyacinth, so miners thought they were rubies. And it occurs now in many different rock types. It's abundant in the alluvial deposits. Just about any stream in central Victoria you put your pan into, you'll get zircons. Occurs in lots of different rock types. And again, as I mentioned, it's used for fission track and uranium-lead dating. Now, these are some Victorian zircons. Now, there are a couple of locations where you can get the little zircons. These are 2 or 3 millimetres crystals enclosed in the basalt. This is at Lake Learmonth near Ballarat. And a good location for them is the Ridge Road Quarry, a basalt quarry near Daylesford. So you can see these little rounded crystals of zircon, typical, and of course they get weathered out of the basalt over time and into the streams. A few of them are big enough to facet, your gemstones. Sometimes, or quite often actually, they get these really polished, highly lustrous surfaces on them, and they were easily confused with diamonds in the old days. So this place called Diamond Gully near Castlemaine was obviously named because the diggers thought they had diamonds. Now, looking at the distribution up eastern Australia, this is a map from Barron et al. Showing the diamond distribution in the black circles, and you can see they spread all the way from northern Tasmania up to North Queensland. There's a few spots in here in Victoria they've taken a few liberties. I don't know of any diamond occurrences in the Otway Ranges, but anyway, so you take this with a grain of salt. But that's a general distribution. And then if you look at this map, which shows these red patches are the Cenozoic basaltic provinces, as we call them, volcanic provinces, from about 65, 70 million years ago, stretching all the way up the east coast of Australia. So there's a broad coincidence between these and the distribution of diamonds, and as you'll see, sapphires and zircons as well. These two maps just show, this should be a pale blue, it's a bit pale, but the sapphire regions are marked here, where you can get sapphires, and you can see that the diamond distribution and the sapphire distribution pretty much coincide. So there's obviously a relationship between the two. If you look at this map, this shows where the diamonds have been recorded in Victoria, and I'll take you to all these locations in the next part of the talk. Beechworth, Rutherglen, Karapui, Kongbul and Toombul-up I regard as reliable occurrences, and there's some uncertain ones as well. So let's start the tour. We'll start in the northeast. The Beechworth Eldorado district. This is the Ovens district, if you like, they used to call the Goldfield area. And we're looking south from the summit of Mount Pilot, which is a granite mass, not very high, and we're looking over what's known as the Woolshed Valley, where Edward Dunn would have roamed during his late teens, early 20s, begging gemstones off the local diggers. Now, this geological map is going to be useless because the colours have washed out completely, but there's a broad mass of granite in here, and Reedy Creek, or Reeds Creek, rises here and it runs along here and it eventually ends up in the Ovens River. And all along this creek there were diamonds found. You can see the triangles. It's a bit hard to see on this map, unfortunately. The designers like pastels when they do diagrams, and they don't work too well when they're projected. But all along the El Dorado Deep Lead, as it's called, or this Reedy Creek, there were diamond occurrences. Most of them were found near El Dorado when the dredge that was mining tin and gold was operating up into the 1950s, so there were quite a few diamonds found there. These other marks where diamonds, where I put them, are more historic. This is Mount Pilot, and there's a divide runs through here. So there were south-flowing tributaries, and some of those had diamonds in them, and there were north-flowing tributaries, and some of those had diamonds. There's one here in the Lancashire Lead, just marked there, and there's another one in Mount Pilot Creek. I can't see the spot there, but there's a diamond in there. And then up here in the Great Southern Mine up near Rutherglen, there were diamonds found as well. So you have diamonds going north and south. Now, in here, you can't see it, but there's a little patch of Permian glacial deposits, and this has often been thought of as the source of the diamonds. They were brought in by glaciers, and we've had mining companies looking in there for them and not really finding much. And even if there were, it wouldn't explain how you got diamonds north of the divide as well as along here. So we don't know where the diamonds came from in this area. They've been brought in. Looking at Reeds Creek, or Reedy Creek, it flows all through granite. It flows through a gorge, and then it opens out into this rather more open country. It's acted like a giant sluice box for gold and tin, and for the diamonds. And as you'll see, well, here are the diamonds, some of them. These are Edward Dunn's diamonds. He got these during the 1860s. And the largest here is about nearly a carat, and it's about 5.5 millimetres across. This is the biggest one known here. It's 8 carats. It's in private collection. It was found in 1977 when a collector just dug his a greased shovel into the gravels in one of the creeks and pulled it out, and there was this diamond stuck to it. So, some features. They're all bright and shiny. Mainly between 1/2 and 2 carats. The largest, as I said, is 8. They're white to pale yellow, and they're rounded tetrahexahedroids. They're just cubes with pyramids on each face. So there's 24 faces on them, and they're an octahedra. So they're rounded crystals. Some have these prominent brown and green spots, radiation spots. Now, these are caused by the diamond being held next to a radioactive mineral for a long while, for millions of years. And then when they turn, these green spots turn brown when there's a heating event of some sort, like a bushfire or a lava flow. So the Beechworth diamonds, or the El Dorado diamonds that show these things, they've got a history there. They're telling us something which we can't quite work out because there's not much evidence for it. They show all sorts of different surface markings depending on their history, and they also have some inclusions. Accompanying the diamonds are sapphires. So these are from Edward Dunn's collection. A bit washed out, unfortunately, on screen, but they're generally dull blue to bluish grey. Very few of them are gem quality, but they're quite distinctive. If you showed me a photograph of that, I'd say straight away they're from Beechworth. They're up to about 7 or 8 millimetres. And there are also zircons. These are typical reddish-brown colours, but also quite a noticeable fraction of these pale white or pale pink sometimes zircons. Now, we've done some fish and track aging or dating on these, and the reds and the browns give 5 and 19 million years, so they've come out of volcanic rocks around about that age. But the 216 million years is quite interesting because that's Triassic age, and we don't know of any Triassic volcanism or in the area, but the only Triassic rocks, the igneous rocks, are in the Benambra region further to the east. So again, this just illustrates this area has become a giant sluice box for gems. Now if you look north of Mount Pilot to Chiltern Rutherglen, this was where there was a lot of mining went on, but it was underground in the sense that it was not surface workings, and these were deep leads for tin and gold. And between 1909 and 1914 there was probably up to about 20 diamonds found in the Great Southern Gold Mine. The largest up to about 5 millimetres. The museum has 9 of these, and just that shows how bright and lustrous they are. A little bit different. They look a little bit different to the El Dorado or the Beechworth diamonds that I just showed you. And these have been some of them have been looked at by Jane Barron and Larry Barron in New South Wales, who are diamond experts in the Eastern Australian stones. And the features they show, some of the features they show, they're as I said, they're bright and they're twinned. That colour, that range in size. They also have some large indentations where they've been growing up against some other mineral. They don't have any radiation spots, and they have various inclusions. And these just show some of the inclusions that are present in the diamond. And you can use a technique called Raman spectroscopy to get some idea of what these inclusions are without destroying the diamond. So that's Beechworth El Dorado. Now we'll move to Toombul-up district. Some of you probably never heard of that. It's pretty remote. It's Ned Kelly country in a way, and it's rather eerie. This is Madhouse Road, the road leading into it. It sort of gives me the feeling that it might be another Belanglo forest sometimes, to use a very bad, but it's the sort of thing, anything can happen up there. But it's a very popular area with the gem fossicas, but not a place you want to camp out overnight, I don't think, for some reason. Looking at the geology, again this is faded out a bit, but the colours are a bit stronger. What we have here is the pale mauve colour is Devonian igneous rocks or volcanic rocks. The pale rocks to the south are younger rocks, the Mansfield, they're carboniferous rocks, sediments. But the key thing is these patches of orange, which are old basalt, remains of old basalt flows, and they sit on the interflow or the interflows between the creeks, the Stringy Bark Creek, Hollands Creek, Webb's Creek and Ryan's Creek. And the basalts they've been dated around about 40 million years old. We've got a date on those. Now if you look at that cross section here, there's a cross section marked by that red line, and we can just have a look at the geology. Again, it's a bit washed out, but here's the basalt sitting on the top, and there are some sediments underneath it. And these are quite young. These are called the Eocene, around about 40 million years old, so a bit older than the basalt, which is sitting on top. And here are the creeks. That's Stringy Bark, is it, and Hollands Creek here. And you can see there's some little patches here marked of gravel, just on the side of right above the creek, and then there's the creeks themselves, which have obviously got gravels in them. Now, this is the material. You can go and sink your hammer into this stuff here. It's clay material in the creek bed with quartz pebbles in it. And then if you're lucky there's a bit of water, you can go and pan. This is Dermot. I think he's obviously looking at me and saying Dermot of Sapphire's blue, something like that. But this is very, as I said, this is a very popular area with the gemstone, because you can just basically dip a pan in and get something. Now, I'll just go back. I noticed here a pea-sized diamond was reported in the press in May 1896, when this was a small gold field, very remote. Didn't last for very long, and it was found at a place called Puzzle Gully, which is just we've positioned it just here based on the reports. You can't get to that site now; it's just thoroughly overgrown. But So it remained, even though the identifications were quite reliable at the time, the diamond hasn't survived. Well, it may have, but we don't know where it is. I regarded it as a bit uncertain until 2008, when the son of a prospect, a fossicker up there, found this little diamond. It's 2.5 millimetres across, about a 20th of a carat, and after a little bit of persuasion, he gave it to the museum, so it's in our collection. Didn't need much persuading, just a bit of publicity is all that matters. So this is it. Quite a nice little obvious diamond with some crystal features. But perhaps the more attractive are the sapphires and zircons which occur in all the creeks. These are typical of the stones, the gemstones, that you can get up to about 12 millimetres or so, these browns and blues and pinks. The reds will be zircons, but you can see there's quite a colour range. Some of them are gem quality, you could facet them. And there are also zircons, pretty similar in colour to the ones at Beechworth. And we have fish and track ages on those, 3.4, 20, this is without errors, I'm not putting errors in here, 31 and 40 million. If you remember, I mentioned that the basalts in that region are around about 40 million years old, so those ones tie in well with the local geology. But there are a couple of interesting occurrences in these Toombul-up gemstones, and these are these sapphires here, which are greens and browns and greys, fairly dull looking, but you'll see they've got a sort of a dimpled surface. It's not smooth, like these, for example, which I'll get to in a minute. But these are not I don't think these are water-worn. I think what you're seeing there is the sapphires dissolving a little bit, etching, if you like, in the magma before they get to the surface. So the fact that these surfaces haven't been removed during erosion or transport suggests that there's an eruption point where they're pretty close to that area in Toombul-up. Finding it would be tricky, but this is what the existence of these stones suggests. Also, these beautiful plum-coloured stones, highly polished, transparent, up to about over a centimetre. These are garnets, but they're a particular type of garnet. They're a magnesium-rich garnet called pyrope, and pyrope is traditionally regarded as one of those minerals which may indicate or can indicate the presence of diamonds, particularly the diamonds which have come from kimberlites, the deep-seated diamonds. So these are a bit of a mystery, but just add to the intrigue of that particular area. Now we're going to move south and then west. I mentioned Donnelly's Creek before. It's a bit hard to see, but it's north of Walhalla. It's this little creek here, runs into the Aberfeldy River. It was a remote goldfield in the 1860s, 1870s. It's amazing what they got into. This is Mount Useful up here, and it's got a patch of basalt on it. Now, Donnelly's Creek was noted for its green sapphires, and I think that's the surviving one. That's one in the Natural History Museum in London. Probably, it's not very big, about 5 millimetres or so, but it's green, and I suspect that's from there. This is looking down from Mount Useful down into Donnelly's Creek, which is the valley in here. So the only way the sapphires, to me, could have got into Donnelly's Creek is down this drainage here, and they were deposited in here. I'm not sure the age of Mount Useful, but that's Donnelly's Creek. Now, closer to home, the Dandenong Ranges, quite a lot of gemstones in the Dandenong Ranges. Most of the creeks, Menzies Creek, Hardy's Creek, Cockatoo Creek, Cardinia Creek, Gembrook Creek, and this creek here called William Wallace Creek, have all got gemstones in them. And you'll notice the geology is a bit similar to Toombul-up and Tatong area that I showed you before. You've got volcanic rocks, granite, and then sitting on top, you've got they're faint, but you've got these patches of basalt, remains of basalt flows, and they have sediments underneath them as well. But these are only 20 million years old, whereas the Toombul-up flows were 40, so these are about half the age. But these almost certainly will be the source of the gemstones. Now, I mentioned William Wallace Creek because in 1868, Reverend Bleasdale, George Ulrich and Alfred Selwyn, who was then director of the Geological Survey, took a dray trip. They took a dray trip from Berwick through the remote wild country along Bowman's Track, which had just been opened, and they got to William Wallace Creek, which was being mined by a few people for tin. And they camped overnight, and the following morning the local miner, one of the local miners, panned some gemstones for them. And Bleasdale described that trip. He wrote it up in Colonial Monthly in 1868, in October, and it's quite intriguing to read his account. I'd have loved to have been, if I could go back in time, I'd just love to have been on that dray, listening to the conversations that went on between Ulrich, Bleasdale and Alfred Selwyn. It would have been fascinating. The best location in this area is Cardinia Creek. It's a location which was basically discovered by the gem fossickers in the 1960s. I don't know how they found it, but they did. Now it's drowned by the Cardinia Reservoir, so you can't get to it anymore, but the sapphires are quite beautiful, ranging from these bright red ones, possibly maybe get to rubies, but then a range of other colours, and some bright blue ones from Cockatoo Creek, which is further to the south. Skirting over South Gippsland, there are some nice sapphire occurrences, historic ones anyway, around Foster, some of these rather unusual orange ones. The Bass River near Kerno, which Edward Dunn visited, and he collected sapphires there. You can still get to that creek if you don't worry about the snakes. Even on the Mornington Peninsula, there's a couple of locations for good sapphires. Toombul-up Creek, which is seen in here, and the beach at Point Leo, which is here. Here you can just see the sapphires and zircons in the sand at the highest level of the beach. And this is Toombul-up Creek itself. And they're probably coming out of the basalt, the older basalt, which forms a lot of the Mornington Peninsula and Phillip Island, and that's they're in around 40 to 50 million years old. I'm not going to concentrate too much on the Daylesford-Trentham district, but there were some really nice sapphires came out when gold was being exploited out of what was called Jim Crow Creek in the 1860s. Bleasdale recorded sapphires, and there's a whole range of zircons as well, some really colourful zircons from creeks in those areas. But now we're going to the far west, a place called Congbul, or on Mathers Creek. This is Mathers Creek. Now Congbul is between Casterton and Balmoral. I don't have a map, but and there's really not much geology there. But let's need to go back, I think. Yes. In 1895, some diamonds were found, reported. One of them was a pale yellow octahedron, 3 millimetres across. It was sent to Melbourne and examined by experts so to speak, and confirmed as one. Where it is now, no idea. If you go to that area now, there's a few trenches, dumps, shafts, and what they were digging for gold was this gravel, cemented gravel, just quartz grains and cemented by iron oxides. Not much to look at, but they think they found a diamond there. And there's some credence given to that if we move to the next location, which is Karapui. Lovely name, not quite sure the derivation, but that's a bit further east from Congbul. It's also had shallow diggings for gold in the 19th century and also in the 1930s. And those diggings were in these sediments marked by these yellow patches. And these are quite young, or relatively young. They're given the name White Hills Gravel. They're gold bearing all over the western part of the state. They represent old river or floodplain deposits back during the Cenozoic period, not quite sure how old, and they sit on the bedrock, which in this case is metamorphosed sediments forming schists, the Sonata group, and there are some granites as well. Now, mining companies were exploring in this area for gold, and a gold mine opened up here near Karapui on this patch here, and here's taken in the 1990s. This is the mine area itself, just easy to mine, just bulldoze it into heaps, and this was the base of it. This, you can see big quartz pebbles sitting on the weathered rocks underneath, and this was the layer in which the gold occurred, and as it turned out, the diamond that was found in 1993 by a student who noticed it bouncing across the separating table in the works. Must have had a keen eye or was very bored, but he noticed it. This is the diamond. It's about half a carat, 4 millimetres across. It's rounded dodecahedron. It's got some unusual markings. It's obviously been battered around and travelled a long distance. And that's now in the museum collection. We paid, I'm not sure how much we paid for it, probably too much, but at least we have it. Now, where there's one diamond, could well be another one. So when the mine closed a few years later in the mid-1990s, the company was called Southern Border Gold, they had some concentrates left. And this is the concentrates in rusty old 44-gallon drums. So we said to the mining company, could we please have those? And they said yes. So we were intent on looking through those concentrates to see if there were any more diamonds in them. First we had to move them, and I'm sure Dermot remembers this very well. We had to get them from Karapui to a processing place near south of Dandenong, south of Ballarat, where there was water, power and a bit of space. And we hired a jig, and with a bit of manpower and some improvising, we processed those concentrates into a number of different fractions. And to cut a long story short, over the next few years, various people sorted those concentrates under the microscope and hand-picked out some minerals, a lot of minerals of interest. To me, the most interesting ones, we haven't found another diamond, by the way. The sapphires are of most interest. Here's the range in colours. I've just selected a whole lot of groups there. They're pretty rounded, not very many are gem quality, but again, they show that full colour range from pinks. There's a few blues, almost down to colourless. You can pick out more gemmy ones, showing better colours. These are up to about 7 or 8 millimetres across. They're hard to find, but they are there. And you can even get enough to facet. So these are little faceted sapphires from those concentrates, up to about 3 millimetres or so. Blues and purples, and here we have greens, greys, unusual colours. Not the sort of colours you associate with sapphires, and probably not in high demand, as you can imagine, but I find them intriguing for their colours. You can do things with colour, at least investigating it. Generally, it's felt that the deep blue sapphires are due to iron and titanium. They say purple colours may be due to vanadium, I'm not sure about that. Pale yellow due to iron, and obviously the pink is due to chromium. And you can see these are some of the elements which substitute for aluminium in the aluminium oxide structure, and you can see these numbers are in picometers. There's a picometer is 100 angstroms, so you can see these are all roughly the same size. If you substitute a silicon, for example, for an aluminium, you've got an extra positive charge, so you have to balance that somehow with perhaps a magnesium or an Fe2+. But you can see they're all roughly the same size, so some of them will fit into the aluminium oxide structure. And we've done some analyses. These are some analyses from Jacqueline Wong in the University of Queensland, who's been studying these sapphires. And you can see these are measurable quantities looking across the crystals for the various elements. So you can do some quantitative research on these. Now, I did a bit of playing around as well with the compositions. I had these analysed at ANU, and this is the selection of small sapphires I had to analyse. I wanted to get a colour range, so I chose pinks, blues, the intermediate colours, colourless ones, and some funny browny green ones. So I got figures for chromium, iron, titanium, etc. And then I thought, well, I wonder if there's any trends here. And so painstakingly, once I got the analyses back, I cut and pasted them into these groupings: chromium, titanium and iron, starting off with the highest chromium figures here, going down, then down, then down, then down, until I ended up with the lowest ones, 14. So you can see that for chromium, obviously the pink ones are in this grouping. From then on, there's really not much trend with composition. With iron, with iron, you've got some dark ones, a high iron, but down here, why a purple one's got the lower iron, I don't know. And here we've got the same thing for titanium. Again, no real trends in colour. So obviously the colour of sapphires is a very complicated field, and once you get all these different elements going in, you can get any sort of colour you want. You can use these compositions though to get some idea of where the sapphires came from. And this model has been developed by Puka et al., who looked at a whole range of sapphires from lots of different environments around the world, and they came up with plots of iron versus gallium on magnesium content to show that the that you could separate sapphires into ones which had a metamorphic origin from ones which formed in a magma. And I've used those compositions to plot the Karapui sapphires, those ones you just saw, and most of them are metamorphic. That means that they came from metamorphic rocks deep in the crust, as distinct from crystallising from a magma. And you can do the same here with iron, magnesium and titanium, and you can see again most of them fall in this metamorphic field. Now, one other aspect of the sapphires which is interesting is that they contain inclusions and little crystals of other minerals, very small, and one of them is a mineral called monazite, which is quite widespread in Victoria. Monazite, this is composition, it's a rare earth phosphate, forms these quite nice little crystals up to a couple of millimetres across, in quite often concentrated in streams because they're quite heavy, and they also resist being weathered and eroded, being weathered anyway. So you can find these quite often in some of the streams around in Victoria. They can, because they contain a little bit of uranium and thorium, they can be dated. So we haven't yet got enough grains to date these, but hopefully if I can get a few more, an age on these would give us the age of when the sapphires were erupted to the surface. Now the zircons also tell some stories. The concentrates showed that in the concentrates there were two different types. These big 3 to 8 millimetres rounded brownie zircons, quite clear. You could probably facet some of those into gemstones. But there's also this smaller population of bright coloured, probably better, they show better crystal shapes. So obviously two different types of zircon. So what does that tell us? Well, you can play around with these. You can do some uranium lead dating on them, and these were done, this was done at ANU, an iron microprobe to determine the age of these zircons. And for the big ones, these ones, we got an age of around about 68 million years. So that was when they were erupted. And uranium content's around 12. And these images here show a polished surface of these zircons, showing cathodoluminescence. This is like a phosphorescence. And you can reveal internal structures in the zircons. You can see they're quite simple really, compared to the small ones, which show much more intricate patterns. These are the small ones here. Again, we dated them the same method, and they're slightly older, 4.5 million years, and they have much higher uranium in them, 320 parts per million. And just looking at how they correlate regionally, here's the Sonata district sapphires down here. These 2 points are the two ages I've just shown you. We also had fission track datas on them, so they coincide pretty closely. And if you look across the state, from the various regions. We've looked at Beechworth, Eldorado, which the zircon age here. I mentioned the Triassic age and the other younger ages. You can see there's a lot of volcanic activity all the way through, pretty much based on zircon ages. The purple areas, the purple bars, show the ages of volcanic rocks that have been dated. So where you've got volcanic rocks dated and zircon ages, here and here, you can see there's a good correlation. Obviously, for the western areas, we don't have that sort of information, but all we can say is that the zircons from the Karapui region could well have come from volcanic eruptions around that time. There were other minerals in the concentrates. These are not gemmy, but they're important in the story. Pseudo-rutile schorl, which is a variety of tourmaline. Spinel, which comes out of the basalts as well. Rutile, anatase and andalusite. I won't discuss those, but they are important. These all come from the country rock. They've weathered out of the surrounding rocks. They haven't been brought in. Now this model looks complicated, so I won't go through it in great detail. What it's meant to show you is what's happened between the late Mesozoic, around about 70 million years ago, and here's the land surface, the dotted line, if you can see it, coming down here. Highly exaggerated, of course. You had an old land surface up the top. You had volcanic eruptions. Is it showing or not? No, it's not. It's weakening. Volcanic eruptions here, 68 around 70 million, and they were contributing the zircons, the sapphires, and possibly the diamond into the local streams. Now, as the landscape was lowered through the next 60 million years or so, it went through different intermediate stages. So, gravels in rivers they were cemented, and they became high-level plateaus. So here, for example, in this next level down, which is not showing up, where's my pointer gone? You had an intermediate stage. So what this really means showing is that you could recycle these gemstones from one landscape to the next. So here's the intermediate one, this one. And you can see this originally was a river valley. Now it's a high point, and the gravel's perched up high, and it's been eroded and shedding gemstones again into the next stream in the sequence. And then eventually you end up with the present day surface, the Karapui. Here is the high level gravels which are being mined. It was originally a river floodplain, which has now been eroded away a bit and just left the remains. So this is meant sort of, it's a bit of a landscape reconstruction, which you can get from the gemstones. So, some conclusions. Victorian diamonds came from near and far, obviously, and there's no local source rocks that we know of. The distribution of diamonds, sapphires and zircons in Victoria are similar to other Eastern Australian fields. We know they crystallise in various rock types deep in the crust. We're still not quite sure what they are. There's a few hints, but there's not a lot of hard evidence, a bit conjectural. And they were brought to the surface during this alkali Cenozoic basaltic volcanism. I haven't gone into this in this talk, but the remnant inclusion pressures, this is the Raman technique applied to diamonds, suggests that these are the subduction diamonds. They're the result of arc continent collision, and they're not formed by crystallisation below an ancient craton like the West Australian ones are. And it's possible to do a bit of landscape reconstruction from, if you know the gemstones and their ages. And just a bit of a setting here. I won't go into this. This is the subduction model, very simplified. Ocean crust is pulled down under the continent. If there's some organic carbon gets caught up on the slab, then it's possible, if the centre of the slab stays cool enough, that you can crystallise diamonds at shallower depths than you would be under the normal kimberlite or crotonic diamonds. So we have to have some explanation for why there's these diamonds up the East Australian coast, because the crust isn't thick enough. And this is a recent diagram showing the various slabs of crust, slabs of sediments that have been pushed onto the Eastern Australian side of the Eastern Australian continent at various times during subduction episodes. So there's quite an extensive knowledge of what's gone on during the Paleozoic period, and the diamonds are obviously associated with that. Now, to finish up, we just need to look at Bleasdale. Go back to John Bleasdale and his collection. He displayed his collection in 1865 downstairs, as I mentioned. He exhibited at a number of other important exhibitions in Melbourne and probably in Paris. He exhibited in Philadelphia and was an award winner in 1876. We don't know whether he took his gemstones to California in 1878. He didn't leave a will. He basically died a pauper. He was in ill health, and no gemstones that can be attributed to his private collection have survived. However, there are a couple of little traces. This little gemstone is a little ruby, as he called it, about 4 millimetres long, which George Ulrich sketched. And it came from William Wallace Creek, where they visited in 1868. Now, whether it was found at that time or not, I don't know, but it's in the museum's collection. It's got Bleasdale's, Ulrich's and DNA fingerprints all over it, so it's highly valued, even though it's only 4 millimetres high. He also did an exchange with the Natural History Museum in London in 1873. I'm not quite sure what he got in return, but he left some diamonds, he left sapphires, including a faceted one. I suspect these are mainly from the Ovens district or Beechworth. These are not original labels, unfortunately. I don't know, and they didn't have any details about the arrangement that was made for him. And these are a number of other gemstones in their collection that he deposited, probably all Victorian. And this is a little green sapphire, I suspect, is from Donnelly's Creek. When he died and was buried in San Francisco, his grave was, like thousands of others, was disrupted during the 1906 earthquake, and so they were all reburied, and no one knows where he is at the moment. So finally, just to show the story continues. This little parcel of gemstones were given to the museum a couple of months ago, given to us by a gold panner in the Bullenwald district down in Gippsland. Nice little blue sapphire, a little rounded zircon. These are anatase crystals, titanium oxide, and this is probably a little monazite crystal here. So you can still find them if you're careful enough in a lot of the creeks in Victoria. And some thanks to people for this talk. There are a lot of people involved, too many to probably list all of them, but for the photography, for the diamond studies, for fieldwork, Dermot and Julian Hollis in particular, and then people who are involved with helping with the analyses and with the mineral separation, and of course this chap here who let us have the concentrates. So that's the story of Victoria's diamonds, sapphires and zircons up to the moment. I hope you enjoyed it.